presentations on heat pumps. I think it's a fantastic opportunity for us, but we're moving back more to traditional refrigeration topic now. I'd like to join Jan in congratulating kgh on their 50th anniversary, a jubileum this year. It's a fantastic achievement. My company is going to enjoy our 50th anniversary next year. The work that I'm presenting here was presented in 2 presentations in Montreal at the kgh-Kongres in August, and I'm developing this work further for a conference which I'm involved in my hometown of Glasgow in Scotland next July. I've not yet written the paper for the conference in July. The deadline is January, so I know what I will be doing on Christmas Day in the afternoon after lunch, because deadline is looming. But it was very good preparing for today for kgh, getting my thoughts in order and helping me with the preparation. So this is by way of a series, if you like, and if you want to hear the conclusion, you need to come and let me welcome you to Glasgow next July. I look forward to seeing you there. However, for the moment, we're looking at the work so far, and really the objective of the 2 presentations in Montreal was to open people's eyes, firstly, to the opportunities to use information that's around us already, and secondly, to try to raise awareness of the missed opportunities, because there is a lot of information available. So I'll give you a flavour of that in this presentation, and if possible give you a hint of where I'm wanting to arrive at in the longer term with this work. So what's in the menu? We'll be looking at why industrial refrigeration systems are not efficient at the moment, and I think they range from really quite good to absolutely dreadful, absolutely shocking in terms of efficiency. But there are reasons for that. I'll look at some new energy monitoring methods and some, I call them new analysis techniques. They're not really new at all. What's new is looking for ways to apply them to industrial refrigeration systems, but they're well-established techniques. And then try to draw together some conclusions and some next steps. So reasons for inefficiency, I described the first one as system architecture. We're constrained when we build the system. Sometimes the machinery room is at one end of the site and the freezer chamber is 100 meters away or 150 meters away at the other end. And there is a cost to be paid in transferring the refrigerant from one end of the site to the other and back again. Sometimes it's a failure to minimize the heat load that's applied to the refrigeration plant. If you allow your cold store to operate with the doors open for a very long period, your energy bill will be high. If you don't control the compressor well and you have 4 screw compressors all running on 25%, then your energy bill will be higher than it would otherwise be. If you allow your suction pressure to be too low, we already heard about this in Pega's presentation at the beginning, there is a penalty to be paid because the system has been designed in a way which means it has to operate inefficiently. So all of these kind of come with the design. If the designer had really focused on this, maybe you would get a better result, but as a system operator, it's served up to you. You're just faced with what's in front of you. However, the next 2 I would describe as operational constraints and operator preferences, and these are really 2 sides of the same thing in some respects, because sometimes the operator will say, well, of course we have to run all 4 compressors on part load because we want to be able to respond quickly to a change in loading, or we have to run with the doors open because there's so much traffic in and out of the cold store. So they're calling it an operational constraint, but in reality, they have chosen to do that. It's their preference to run the system that way. And really, what we need to be much more vigorous about pursuing is that it does not need to be that way. You can take steps if you're focused on energy to reduce the impact of doing these things. So is it operator preference or is it operational constraint? Maybe 2 sides of the same thing. And then finally, in this section, it seems a strange thing to say in this day and age, a lack of information, because in some ways we've got more information than we ever had before. We've got all the telemetry, monitoring every possible aspect of the plant, recording data minute by minute or even second by second in some cases, and storing it and then bringing it back out again. It's not so much a lack of raw data, it's a lack of the ability to do something with that mountain of information. And I think 50 years ago, maybe even 70 years ago, plant operators in many cases were actually better at making more use of the little bit of information that they had. I have a logbook in my office from an ice making plant from 1955, where every day the operator went and wrote down the operating performance of the plant, and he calculated how many, this was in England, how many pounds, shillings and pence it cost him to produce a ton of ice every day, and the cost of production every day was recorded in the engineering logbook. Most of my customers today don't correlate production output and cost of production with energy efficiency of refrigeration systems. So we've lost something in the last 70 years. We're not as good at it as we used to be. So in that sense, it's a lack of information. So that's the challenge that's facing us today, and what I want to try and do in this work is to raise the possibility for us to do rather better than this, because I think energy performance of refrigeration systems is actually the biggest challenge that is going to face us in the next 15 to 20 years. So how is efficiency measured? Well, often it's not. Some sites don't even have a power meter, believe it or not. Or if it's there, it's not calibrated, or it's not actually working, or nobody goes and takes a reading from it. So the meter is whizzing around, but what was the reading last month? We don't know. What is it today? We don't know. It's just being ignored. Maybe a single power meter serving the entire site, including refrigeration system and heating system and fork truck battery charging system and lighting system and ventilation system. Or perhaps there is a current meter for each large user on the site, maybe a meter for each compressor, for each pump. Probably not small pumps and fans, that would be very, very expensive and of limited benefit. Maybe it's measuring the instantaneous kilowatt hours being consumed, and that number jumps up and down, goes all over the place, and doesn't really mean terribly much. Maybe better to be aggregating that figure on a daily or a weekly basis and recording the kilowatt hours used, for example, in the previous 24-hour period. For example, by having a meter that gives a pulse output every time there's a kilowatt hour or 10 kilowatt hours, and simply a PLC counting pulses. It really is that easy. Or maybe it's even more sophisticated, a full electrical supply, monitoring all aspects of the usage of every major user, the power factor, the phase angle, all of that good stuff. And I would say that's a range from zero cost to implement through to really quite expensive, but you don't have to go all the way to the fully quite expensive. I would suggest that recording kilowatt hours on a regular basis is, for each major user, is the level that you should be pitching at. Less than that doesn't give you enough useful data. More than that probably gives you too much information and is of limited value because of that. So some other initial observations about the monitoring. And Pega talked a bit about COP, and Alex gave us an optimist view of COP for heat pumps. I don't entirely agree with him. There's a different way of looking at it, but that's a different discussion, as you said, to be taken offline for later. But here's the thing, COP is not a good measure of cold store efficiency. Just think about this for a minute. I've brought up on COP, this is how you measure how good your refrigeration system is. Measure the W, measure the Q, divide one by the other, gives you the COP. If it's a big number, that's great. If it's a low number, that's not so great. That's not the way to measure your cold store efficiency. You could make the COP of your cold store better by leaving the doors open, because then the room would fail to reach temperature, the compressor suction would rise, and the compressor would give you a better COP, but it would run 24 hours a day, 7 days a week, 365 days a year. It would be very inefficient to run your cold store that way. So, as I say, it's easy to imagine a very bad system, a cold store with the doors open, that's got a good COP. So COP isn't actually that helpful in that type of application. I would far rather, if it's a pie factory, tell me how many kilowatt hours per pie, or if you prefer, how many pies per kilowatt hour. If it's a brewery, how many barrels of beer per kilowatt hour. If it's a cold store, how many pallet movements per kilowatt hour. You've got to relate it to production throughput of one kind or another to get a measure of whether it's efficient or not. So, measuring refrigeration performance and not relating it to business performance is also not useful. And I can't think of any of my customers who do this well. The refrigeration technicians look at the refrigeration system, but they don't gather data on the business aspects. The accountants do that. And the accountants and the engineers generally pass each other on the other side of the street. They don't converse with each other. They don't share information. So how can they keep their whole system operating well if that's the case? So no connection between business management and plant management, I think, is a fundamental flaw that far too many people are guilty of. There are ways of doing it. You could do it automatically, or you could have a sort of process for doing it, a weekly meeting perhaps, to share data. But it's almost never done. And that's a major lack. So we've been looking at energy efficiency and tabulating how this is for cold storage facilities and chilled storage facilities of various types. And the yellow line is the upper line is a line that was produced by the British government in the mid-1990s of what best practice might look like for cold stores. And once you get above a certain size, once you get above about 150,000 cubic meters of cold storage space, they said if it's using about 30 kilowatt hours per year per cubic meter, we'll call that best practice. But the dots on the graph are examples of cold stores that have been installed since then that are better than best practice. So the old best practice line is out of date, and I find that quite challenging. It's a good thing, but the challenge is how much better could it be? It wasn't an immutable law of physics that said it will never be better than 30, but it was kind of treated that way because that's the downside of publishing something and calling it best practice. Somebody says, well, I got to 31, that's nearly best practice, I must be doing really well. And in reality, they weren't doing really well at all. The blue line is what I presented in Montreal as what I believe best practice for cold storage is in 2019. And you can see there are some sites that are achieving that line. There are others that are somewhat higher. It's a very crude measure. If a store is very busy, then that number will be higher. If it's a very old fabric, that number will be higher. And the solution of knocking it down and building another one is fairly drastic. So it is a best practice line. It may even be possible to be below that line, but that's a sensible target line to aim for. And you can see it's radically different to the old best practice line. Now the reality is that average stores, this is from a survey done about 5 years ago, right across Europe, covering about 700 facilities, the average is much higher than the yellow line. And there are some stores that are operating towards the best practice line, but there are many that are consuming 2 times, 4 times, even 8 times more energy than the best practice line. And I find that really quite shocking, quite disturbing, because it's difficult to see how they can possibly be that bad. Not only is the plant running very efficiently, it's also grossly oversized and running very inefficiently. So we're getting it wrong right the way down the line on so many levels, right from initial concept through to ongoing service and maintenance. We're not doing it right. So, some ways of analysing data, and none of this is new, but I just want to put it in front of you because it might open your eyes to some of the possibilities. This is a graph taken from the government weather station that is very close to a cold store that we maintain in England. So this is the ambient temperature, the ambient dry bulb temperature for the neighbourhood in which the cold store is. And this graph is the daily kilowatt hour usage, as I said, recording kilowatt hours used every 24-hour period and plotting it on the same time base. And you may remember, maybe 20 years ago, former American Vice President Al Gore presented a video film called An Inconvenient Truth. And he showed 2 graphs and he said, do you think these 2 ever fit together? Now his graphs were of global temperatures and CO2, and he was comparing them with the coastline of West Africa and the coastline of South America and saying, do you think these 2 ever fit together? But clearly there's a bit of a relationship between dry bulb temperature and kilowatt hour usage. When the temperature goes up, the usage goes up. well, that's fairly obvious. Maybe everybody already knew that. However, if you actually correlate one against the other, it's not quite as good a fit as you might think. There's a huge amount of variability in there. So the blue dots are every day on the previous graphs, with the ambient temperature data along the x-axis and the energy per day axis up the y-axis. And yes, you can see it tends to increase as the temperature increases, but the curve fit is pretty sloppy. You know, there's a high variability there. So there's more to it than that. It varies actually by plus or minus 50% of the daily figure. It's a huge variation. If you use that best fit and back it out, then you can see that there's more of a flat line, but still with a huge amount of variability. So it may be that the smoothing inherent in taking a daily average temperature is kind of knocking out something more pertinent that's happening. You know, one day might have averaged 10 degrees because it was very cold in the morning and very hot in the afternoon, and another day might have averaged 10 degrees because it was 10 degrees all day. So you need to be careful with the data that you're looking at. Secondly, looking for recurring behavior in the pattern, and that's things that happen on a regular basis. And an example of why this is important is we had one cold store operator who spotted, when they were doing this kind of analysis, that every morning at about 6 o'clock there was a spike in their plant kilowatt hours figure. And they discovered that the guys at the end of the night shift were opening up one of the big doors in the cold store and going outside for a smoke and leaving the door open. It was absolutely crazy, but they were able to detect that this was happening because they saw a blip on a daily basis in the data. So it could be shift worker behavior, it could be other external influences. All sorts of things will cause recurring behavior. And of course there will be recurring behavior. We all go home on a Friday evening and business dips down Saturday, Sunday, and then we come back on Monday morning, for example. Or perhaps there's a big delivery comes in on a Tuesday, and it happens on a Tuesday every week. What you're looking for are the other recurring patterns that are not really meant to be there. So when we do noise and vibration analysis, we take a very spiky, shaky waveform and we perform what's called a Fourier analysis to it, a mathematical technique to turn it into a family of sine waves. And by analysing the frequency of the sine waves that build up to make the overall pattern, you can see what the recurring behaviours are. And that's very useful if you're measuring the vibration on a compressor bearing or the noise emitted from a condenser fan and that kind of thing. So it's usually used to spot tones and noise signals or vibration systems. But you can also apply it to this daily or hourly or minute by minute energy data. And it's quite interesting what you see when you do that. When you do the Fourier transform, you can see that there's recurring spikes going backwards. You need a lot of data to do this, and the more data you have, the better correlation you get. But there's a lot of false information being presented here because actually this was a recurrence that was happening once a week, once every 7 days. And you can see there is a spike at 7 days, but there's also a spike at 3.5 days and 2.33 days. These are artificial. This is because it was a pure, like a delta Dirac function, a spike. And if you model that as a series of sine waves, then you get a recurring pattern. If it was more like the weather data, then you would only get a single, and I'll show you an example of that in a minute. So there's data from some real kilowatt hours figures that I took from one of our monitored sites for a 3-year period. And you can see it actually goes off the scale when you get to 365 days, which says there is some kind of an annual performance thing going on there. I took that real data and I played with it. I put in a 20% increase once a week. So it wasn't to the same value, it's just that I made Saturday 20% higher than the others. And that's what I got. You can see there's a spike at 7 days, but we've got those pesky spikes at 3.5 days and 2.33 days as well. So it is indicating something's happening. Oddly, I then went back and I made Saturday 30% less than the other days, just to multiply the Saturday numbers by 0.7. And you get exactly the same thing. You get a spike at the 7 days and the 3.5 and 2.33. It's because of the mathematics. It doesn't matter whether the recurring thing is an increase in energy or a decrease in energy, it will show up as a spike when you do the Fourier analysis. You need to be really careful about what you're doing here. So it's important to match the sampling rate to the time span that you're looking at. If you're looking for something that's happening on an hour-by-hour basis, you need to be measuring on a minute-by-minute basis, and you don't want to be looking at more than a week's data. If you want to see something that's happening over several months, then you can't do it on a minute-by-minute basis because you just end up with too much data. So you want to gather the data at very high frequency, probably every minute, but then do some pre-processing to group it together into hours or days before you perform the analysis. And if you're doing it as I did, just using a spreadsheet, which is really quite easy once you get your head around what it's doing for you, you're limited to having 4,096 data points. It needs to be a power of 2, so you could have 2048 or 4096 or 512 or whatever. You want to have as many as you can, but it needs to be a power of 2 for the spreadsheet to be able to do its magic. And if you've got 2 recurring things in the same frequency, maybe something on a Wednesday and something else on a Saturday, you'll only get 1 spike for that. So all it's doing is saying something weird happening here, you need to go and investigate, but it's a useful flag to raise. So the conclusions are, firstly, collect meaningful data. There's no point just having a single power meter if you want to do anything sensible with the information, because that's really not any help at all. You need to have sufficient memory in your system to record the amount of data, and this could be gigabytes of data on a daily basis if you're really taking it seriously. And comparison is very useful. This is the real key, is compare compressor 1 with compressor 2, compare compressor 1 today with compressor 1 yesterday, compare compressor 1 today with compressor 1 last year, last month, last week. It's the comparative thing that really adds value. So you need to be gathering lots of data and then being able to draw it back again. Look for correlation to ambient, obviously, but look for correlation to other things like business activity. And beware of what's called aliasing, which is where you've got one input but it gives you lots of outputs, like in the Fourier analysis, or maybe you've got multiple inputs and you only get one output. As I say, record frequently, but do some pre-processing. And we've been doing this for the last couple of years, and it's really given us some valuable, fascinating insights. It's been able to spot, for example, that the volume ratio on one screw compressor on a site with 6 had been adjusted at some point, and it was not performing as well as the others. And when you just looked at the raw data, that was buried. But when we did the analysis, it came out clearly, and that saved us about 12% on the energy performance of that compressor just by setting it back to the place where it should be. It's identified float valves that were intermittently sticking. When the engineer went to look, everything was working fine, but somehow that plant just didn't perform as well as the other one, and it was because it was that kind of intermittent fault that was never there when you went looking for it. So lots of really valuable output from doing this, and that's what I want to develop further and look at ways in which we can capture that and make it available for everybody. Because as I say, energy is going to be our biggest challenge in the years to come. Thank you very much for listening.